Dear learners, greetings from IIT Guwahati. Now we are back in the course Fundamentals of Compressible Flow, Module 5, Expansion Waves and Oblique Shock. Till this point of this module, 5 lectures has been covered and we have addressed the following topics. So, they are Frankel-Mayer expansion waves, oblique shock waves, theta beta m curves, they are governing equations. Then we discussed about supersonic flow over wedges and cones, supersonic flow over the blunt bodies. Then also we discussed about shock expansion theory, and then we have shock polar and pressure deflection diagram. This is another method in which the oblique shock waves can be represented graphically in addition to theta beta m curve. And one such one particular case was demonstrated with respect to pressure deflection diagram for regular reflections of oblique shocks. So, this is one such common phenomena in which the occurrence is seen in many applications. And some other occurrence of oblique shocks, we can have intersection of oblique shocks, we can have a situation of Mach reflections, we can have a situation of wave reflections from pre-boundary. So, these are the kind of natural occurring phenomena when we have oblique shocks, expansion waves, they occur simultaneously. And in fact, these existence of these phenomena are very vital to understand the flow field in the supersonic environment. So, we will touch upon some of the important aspects of these physical flow phenomena which occurs in natural processes. So, first thing that we are going to discuss is the intersection of oblique shocks. So, in the intersection of oblique shocks, there are two category of oblique shocks we will be dealing with. One is opposite family, other is the same family. So, if I say opposite family, I mean the as I mentioned in my last lecture, we have a left running wave and right running waves, and when both of them interact or intersect, then we can say it is a opposite family. So, one such case was demonstrated was the regular reflections from a solid boundary, in which there was an incident shock which is formed from a compression corner which makes an angle theta, and this incident shock makes an angle beta 1 with respect to this corner with respect to horizontal. Now, there is another boundary which is located and in the upper part. So, this incident oblique shocks impingence on this solid boundary. So, as a result it gets reflected. So, ideally if you look at streamline point of view, the initial streamline in the region 1 which was horizontal now gets deflected after this incident shock by an angle theta, because this inclination surface was inclined by an angle theta, and finally the streamline that has to go out of this out from this reflected shock has to be again parallel to the horizontal surface. So, in the process we have a incident shock, we have a reflected shock, and if you look at observer point of view, we can say the incident shock is a left running wave and the reflected shock is a right running wave. So, these are the oblique shocks of opposite in nature. Now, another situation, and in this case what we had is that there was one compression corner, and whereas the upper surface or upper solid wall is horizontal. Now, we will simply tune this situation for another case in which we have two compression corners. That means, we have a upper wall, we have a lower solid wall, and both have a compression corner. The lower one is at angle and theta 2, upper one is makes an angle theta 3. So, if you look at this oblique shock point of view, both are of course incident shock, there is no reflected shock, both are incident shock, and they both occur on this compression corner. One was with respect to angle theta 2, other was with respect to angle theta 3. So, what we can say, for theta 2 angles compression corner, the oblique shock is denoted as A, and for the theta 3 compression corner, the oblique shock is denoted by oblique shock B. Now, here both are incident shock and they meet at some point of time, they meet at a point E, and in fact both shock A and B corresponds to the same free stream Mach number M1, and they meet at the point E. Now, what is going to happen after that? So, since they meet at point E, say then what could have been happen is that both will be refracted. So, here we will not use the reflection because it is not reflected from the wall, because this both the shocks interact at point E and they are treated as a refracted shock, and refracted shock C and D again are formed with starting point E. Now, when this refracted shock C and D are formed, let us see what happens with respect to streamline point of view. Now, in the region 1, and in first thing what we should remember is that shock A and B are formed for stream of stream conditions, which is region 1. Then but shock C is formed with respect to interaction of A and B, and of course D is also formed with respect to interaction of A and B. Now, remembering this point, so if you want to analyze the flow phenomena with respect to streamline point of view, so let us denote this region as 1, 2 and 3 as shown in this figure. For example, a streamline that comes and interacts with the oblique shock A. So, and because this particular compression corner for the oblique shock A has a flow deflection angle theta 2. So, the shock wave will be deflected by same angle theta 2, that means streamline in the region 2 will be deflected by an angle theta 2, and because of this region it will have a its own shock angle, and this and it will go and finally it will meet at point meet the refracted shock C. Now, another streamline from the same region 1, when it interacts with the oblique shock B, which is a right running wave, and it makes an angle theta 3 and as a compressor corner, the flow streamline gets deflected by same angle theta 3, and after that a region 3 is formed and it now meets the refracted shock D. So, what may have meets these things. Now, after if you look at this particular phenomena, what is happening is that a kind of line is formed that which we call as a slip line. Now, why this concept of slip line arises? Because what may happen is that the ideally when the streamlines that comes out after interaction from refracted shock C and D, and they must be parallel. They must be parallel as and when they come out of the shock system. So, when they have to be parallel, we can see that from the region 3 the streamline is comes out of this, and because of which it has to deflect by a certain angle theta 4, and another streamline that comes out of refracted shock D, it will have another the angle theta 4 dash, and both has to be parallel. So, to make these things more clear, what a concept has been dropped in, what we call as a slip line. So, a slip line is formed which acts as an imaginary surface or a line. In this case it is the line EF, across which two conditions are satisfied. First thing, the streamlines must be streamline must be in the same direction, which is parallel to the streamline, parallel to the slip line. Second point is that after interacting the shock process, the pressures for these two streamlines must match. That means, pressure in the region 4 and 4 dash must match. So, hypothetically saying that region 4 and 4 dash will have, since both have finished the shock interaction process, both will have same conditions, and to match these same conditions imaginary line concept, slip line was introduced. So, and based on this slip line, and since they will have a same angle, they will have same directions, the angle theta 4 dash can be calculated from the information with respect to theta 2, and theta 4 can be calculated from the information with respect to theta 3. And across this slip line, we can have this condition theta 4 dash is equal to theta 2 minus phi, and theta 4 is equal to phi minus theta 3, and phi is the angle which the slip line makes with respect to horizontal directions, and which was of course the original solid wall was located. Okay. So, this is what the concept of a slip line, and now to solve this kind of problem, it is a very iterative process. So, we have to start the process from the region 1 with the angle for Mach number m1 and theta 2, we can get the condition 2 region 2 information. From Mach number m1 and with 3, we can get the information from 3 for the region 3, and to get 4 and 4 dash, we have to rely on some graphical way of representing this particular phenomena, and that is nothing but p theta diagram. So, whatever I have explained, I will just summarize in this bulleted form. So, when the two oblique shocks of different strength originated from the compression corner interact, they are treated as opposite families if it is a intersection of left and right running oblique shocks, and in this case it is A and B. Both are called as incident shocks, and they have different flow deflection angles, and since they have different flow deflection angles and theta 2 in this case is higher than the theta 3. So, we can say here the shock A is stronger than shock B. Now, after the interaction, the shock systems are reflected as C and D downstream of the intersection at point E. Now, the streamlines passing through the shock systems A and C experience different entropy than that of streamlines passing through B and D. This point I just want to emphasize, since across the oblique shocks entropies will be different, and obviously this strength of shock A and B are different, and ultimately the streamlines, when they crossed this shock system, that is streamline in the region, when it crosses shock A and C, it will have a conditions which refers to the region 4 dash, streamlines which crosses 1 and 3 and it will have a conditions with the 4, and ideally 4 and 4 dash should be same, but why we say it should be same, but the entropies are different. Now, to map this entropy difference, a imaginary line, the imaginary line slip line takes the account for the fact that this slip line is a flexible line which can turn which can tune itself, or which can orient itself in such a way that entropy must at the end of these things we can have two conditions that needs to be mapped, that is pressures in the region 4 and 4 dash. Okay. So, this is what the word slip line is used in the when you deal with the interaction of oblique shocks of opposite families. So, the entropy in the region 4 and 4 dash are different. So, in the dividing line EF is formed between the two regions that has entropy changes across a refracted shock C and D in a discontinuous manner. So, across the slip line what changes is only entropy. Now, by definition the slip line will satisfy the following conditions. First, the pressures must be same across the slip line, otherwise it will be a curved slip line leading to inconsistent geometry. Second thing, the velocity in the region 4 dash and 4 must match in the same directions, but their magnitude may be different. Maybe one streamline may have higher velocity, other streamline in the region 4 may be lower velocity, but the directions must be same. The above condition, with the above conditions and properties in the region 1 and as well as the deflection angles for incident shock A and B, we can determine the completely the flow properties for the shock interaction process. So, first thing is that, so to solve this kind of problem, we have to recall this pressure deflection diagram. So, first thing that we have to do is that for the region 1 we have to do the pressure deflection diagram. So, for condition M1, we can have a pressure deflection diagram which is seen by the solid line, and in this case we know this theta 3 and theta 2, and accordingly we can note down the point in this pressure in the M1 curve, locate the point 2 and 3. Now, for once you have 2 and 3, then from point 2 also another pressure deflection diagram can be drawn with respect to Mach number in the region 2. So, this particular dotted line can be drawn for the Mach number M2, and similarly when we can also draw the P theta diagram at point 3 with respect to Mach number M3, and when you draw this independently, and both the curves, for that means after interaction of shocks A and B, that is region 3 and 4, they will intersect at a point 4 and 4 dash, and this intersection point is nothing but the location of the slip line, and location of the slip line, if you can just drop a vertical, we can find an angle phi, and that means we can say that from point E we can draw a line which we call as slip line at an angle phi, and this phi can be determined by this abscissa from this P theta diagram, and once you draw this determined, then we know the directions. So, from this and of course, region 4 and 4 dash we can also find the pressure. This is how the problem is solved, the complete flow properties are solved. So, whatever things I have explained, this has been written here, that pressure deflection diagram is extremely useful to visualize the solution of this interaction process. Corresponding to Mach number M1 on the P theta diagrams, the points 1, 2, 3 can be located. Now, using theta beta M curve, the Mach number M2, M3 in the region 2 can be calculated. So, new P theta diagram can also be drawn with corresponding to M2 and M3. The intersection points between these two diagrams, that is point 4 and 4 dash, will finally determine the final flow deflection angles, leaving the refracted shocks C and D, and the corresponding equal static pressures across the slip line. Now, with the flow deflection angles and Mach numbers in the region 2 and 3, the strength of refracted shocks can be determined. Now, if the intersecting shocks are of equal strength, then the flow pattern is completely symmetrical and there will be no slip line. If they are of equal strength, we won't have the will not have this kind of situations, and this slip line will have, it will be an analogous situation as if it is a analogous situation, that so that there will not be any slip lines and both the streamlines will be ideally horizontal. Now, we will discuss something on intersection of oblique shocks and Mach waves. So, we have already mentioned that Mach wave is the just initiation of the oblique shocks, and the Mach waves are it only depends on the function of Mach number, and if you know the Mach number, Mach waves or Mach angle can be calculated, and Mach angles are normally represented by mu1 for the Mach number M1 and mu2 for the Mach number M2. Now, what is the idea is that what will happen if a Mach wave interacts with an oblique shock. Now, till this point of time we have been talking about that a oblique shock is formed when there is a compression corner, and in this case an oblique shock is shown here, which is makes an angle beta for a compression corner which deflects the free stream by an angle theta. Now, what is happening is that we can have a situation that means because of these regions the Mach numbers are now can be written as M1 and M2, right. Now, one can have or one can find out the Mach angle with respect to M2 and M1. So, in that way we can say that Mach angle for the region for the Mach number M1 can be written as a mu1 and Mach angle for the Mach number M2 can be written as a mu2, and this angle mu can be written as sine inverse 1 by m, and in this case we will have mu1 will have sine inverse 1 by m1 and mu2 will have sine inverse 1 by m2. So, this anyway we can calculate based on the information m1 and m2. So, the question here is that if a Mach wave is formed and this Mach wave somewhere it is going and hitting this oblique surface. Now, what is going to happen? Does this Mach wave has sufficient strength to deflect, or if it hits, what consequence we can have? So, and to analyze this, what we can say here that we have to represent these particular things with respect to velocities, and here we will bring about the horizontal component of velocity u1, and if the total velocity is given by v1, corresponding horizontal component of velocity is u1, and similarly for v2 in the region 2 the horizontal component will be u2. Okay. And from this from our information we can write that this sine mu1 we can write as a1 by v1, where a1 is the speed of sound, and sine mu2 we can write it as a2 by v2. And what we can see here is the fact since it is a supersonic environment, so we can say u1 is greater than a1, that means beta, that means the beta shock wave angle, that means oblique shock angle is greater than mu1, that is quite obvious situation. And here and again but for the region 2 your u2 is less than a2, because the normal component of the flow velocity beyond the oblique shock is always subsonic. This has been proved from the theory of oblique shocks. So, u2 is less than a2. So, this will imply that beta minus theta will be less than mu2. So, beta minus theta is nothing but this particular angle. So, beta minus theta is less than mu2. So, from this geometrical information it is now proved that the Mach wave which is formed with respect to an oblique shock, they must hit, that means they cannot go in other directions. So, once they are formed, at some point of the time they are going to hit the oblique shocks. That means Mach wave is always hits the oblique shock. So, this is the conclusion that we can draw, but in this particular case if the Mach waves are not of sufficient strength, so that after interactions they try to either diffuse or they form very weak expansion waves. So, the Mach waves do not have enough strength to deflect the primary oblique shocks. So, this is the conclusion what we make, and this particular conclusion will be useful for our further analysis. And here the entire summary that I can say is that the Mach waves formed due to an oblique shock, they come and interact or hits the oblique shock, and they cannot diverge any other directions because these conditions are satisfied with respect to geometrical situation, that is shock wave angle is higher than the Mach angle. Okay. Till this point of time we have been talking about oblique shocks of opposite family. Now, we will see that what will happen if we have a situation in which oblique shocks intersect when the shocks are of same family. So, shocks are of same family, I mean that in this case the geometrical orientations are shown in this figure. So, here there are two compression corners, that is which is located by an angle theta 2 and theta 3, and this we call this as a stepped body, or we can have a situation there is one horizontal, the first surface AB makes an angle theta 3 theta 2 and second surface makes an angle theta 3. So, on this particular situation, when the supersonic flow passes over it, it sees two compression corners. So, first for this inflow Mach number M1, we will have a region 1, and from this region 1 a oblique shock will be formed. So, this oblique shock AC will be formed. So, once this AC is formed, the streamline goes and gets reflected by an angle theta 3 theta 2. Now, again it sees another compression corner at point B, so that the streamlines further deflected by an angle theta 3, and so this happens here. Now, when and with respect to shock point of view, we can see that shock A, C and B C meets at the point C, and after that what is going to happen? And these are the two shocks, so they must reflect or refract as another shock or single shock which is known as CD. So, A, C, B, C merges at point C and they come out of a single shock CD. Now, for this situation, if you look at streamline point of view, the streamline point of view when it passes the streamline which is far away from the initial surface of this wall, it now sees only single shock, whereas streamlines which is adjacent to this wall, it goes through two shock systems, that is AC and BC, and streamlines that comes far away, it sees only one shock, the CD. So, then obviously the conditions region another condition which is formed which we call as a 5 for this far field streamline, and the condition 4 which gets generated when this primary streamline gets deflected 2 times and finally it lands up in the region 4. Now, as I said, these shocks are of different strengths, so entropy will also be different, and the combined shock system will give a region 4 for which we have entropy, we have a certain entropy change in this process, and across a single shock there will be another entropy, and ideally it should not match, that means entropy will never match. Since the entropy never match, we have a theory called as the slip line theory formations. So, across a slip line theory formation, a slip line will be generated, and this across this slip line, and this will make an angle phi with respect to horizontal. So, with respect to horizontal direction phi, we can have this slip line. So, the streamlines will now be parallel to this slip line, and the conditions that is going to impose here, P4 must be equal to P5 and theta 4 will be equal to theta 5, and for similarly P3 should be equal to P5 and theta 3 must be equal to theta 5. So, to have this, if you look at this particular shock systems, so region 3 and 5 need not be same, so another oblique shock must form, so that it makes a conditions that the 4 and 5 conditions should map. To have these 4 and 5 conditions to be same, the shock C is also going to form. And this, of course, the merging shock CD is of very high strength, and a weak shock C is formed, which has to be very weak, because it has to go through continuous entropy change, and finally the conditions has to be such that the flow field must match across the strip line. So, because of these regions, we will also have a reflected shock CE. That means occurrence of reflected shock has to be there. So, this is actually the entire flow physics, and if I can explain them, we can write in some bulleted form, that is, when two oblique shocks of different strength originated from two compression corners interact, they are treated as the same families if both are left running or both are right running shocks. Now, in this case we have a two left running shock waves AC and BC emanating from a compression corners A and B. They interact at a point C and they finally they merges as a single shock CD. Now, with respect to streamline point of view, the streamline passing through region 1, 2 and 3 has pressure and flow directions in the region 3, okay, and that are determined from the upstream conditions, that is Mach number and flow deflection angles from the region 1. That means, from region 1 with this theta 2 we can get back information of region 2, from this region 2 and with respect to theta 3 we can get the information, entire flow information for the region 3. Now, let us pause for a point. Then the flow conditions in the region 2 is determined through Mach number and flow deflection angle for M1. The flow fields in the region 3 is processed by dual shock systems AC and BC, while in the region 5 is processed through the single shock CD. Now, since all the shocks will have a different strength, so the entropy change across the single shock will be different from this dual shock systems AC and BC, for which a slip line is going to form, and across this slip line the pressure and flow directions must be flow direction of the streamlines, that is in the region 3 and 5 must match. Now, when 3 and 5 must match, that is, but it is not very easy to map these things, and some natural occurring process should happen. That is, because it is not possible to find a single shock CD that would allow simultaneously give same pressure and flow deflections across two intermediate shocks AC and BC with both systems emerging from same upstream flow. So, this is not a very this is naturally it is impossible process. So, the nature what it does is removes this problem by creating a oblique shock, and he creates an oblique shock at point C and it goes as a CE, and across this oblique shock the CE is a very weak oblique shock, or it could also be an expansion waves. So, that this the conditions region in the region 4 and 5 gets mapped. So, the another region 4 is formed such that equal pressure and flow direction is experienced by the streamlines which are located in the region 4 and 5 across the streamlines. Now, the flow field, so we have all the informations. The flow field is solved iteratively through numerical approach by adjusting the shock CD and CE. That means, shock CD and CE are adjusted in such a way we can have an imaginary slip line, and the conditions 4 and 5 are mapped. So, these things it is very difficult to solve maybe through analytical problems just by referring normal shock table or oblique shock table. So, these complicated flow field features are solved iteratively, and through of course certain numerical approach can be included, so that this kind of problems can be solved. Now, we will move to next important segment, which we call as a Mach reflection. So, it is also another occurrence of oblique shock, and in some instances when the oblique shocks is unable to get reflected from a boundary. So, a Mach reflection is formed. Now, why it is unable to reflect from this from a solid wall? There could be two reasons possibly, because from the theta beta m curve one may not find an oblique shock solutions. As a result, we can say there is a possibility of attached or detached shocks. So, there is a possibility of mainly detached shocks. So, that means the oblique shock solution is not possible. So, in such cases we call this as a Mach reflection. Now, if you recall our previous example, that means regular reflection from a solid boundary, in which there is an incident shock with respect to compression corner angle theta 3 and shock wave angle beta 1, and it gets reflected from a solid wall at point B. So, a reflected shock is formed, and across this reflected shock, again the streamline is back to parallel to the solid wall, and this streamlines is parallel and to the solid one, and this makes an angle phi. Now, what in this particular, while solving this particular problem, what has been assumed or is that your theta, whatever the compression kernel angle, is less than the theta max for M2, that means for Mach number of with respect to M2, and the theta is also less than theta max for Mach number of M1. So, that means we can directly refer the theta beta M curve to solve the problems, and in fact we have solved a problem for these situations and we find a solutions, and you will see that this particular will have a incident shock and reflected shock. Then the Mach reflection situation will arise when we impose a condition on theta. If you keep on increasing theta to a particular angle where oblique shock solution is not possible, then this particular problem or flow situation can be tuned to another situation, what we call as a Mach reflections. So, what we can say here is that a regular reflection of solid wall from a solid wall, the governing conditions follow the fact that flow must deflect through the compression kernel 2 and 3 by a reflected shock, so that streamline is parallel to the upper wall, and in this case it is assumed that deflection angle is less than the maximum deflection angle corresponding to Mach number region 2. Also it is gives an attached shock situation for the Mach number in the region 1. Now, what can happen, a special case can arise when the oblique shock solution is not possible for the reflected shock from the solid wall corresponding to Mach number in the region 2, that is compression kernel causes the maximum theta deflection angle. So, we will have a situation that your theta max for M2 is less than theta and theta max for M1. So, this particular condition gets imposed here. So, when it gets imposed here, this main problem now becomes another complicated situation. So, what will happen, the first incident shock is formed in a similar way as it formed here. Now, here what happens here, and till one point of time it cannot go further because we do not have a attached shock solutions for the Mach number 2. So, a kind of what will can have. So, and if you look at this theta beta M curve, the for the theta max will for the Mach number M1 will have a theta solution here. So, obviously this is an attached shock, and for Mach number M2 it is not an attached shock because it is the theta it is higher than the theta max for Mach number M2. So, there will be detached shocks, and here the nature removes this problem by forming a strong shock, and here you can say it is a normal shock. And this normal shock, if you look at with respect to solid boundary point of view and close to this boundary, it appears as a normal shock and slowly it becomes curved and meets this incident shock, and when this meets incident shock it again reflect as a curved shock, and this particular flow phenomena is such that it takes the shape of a lambda, I mean symbol lambda. So, we call this as a lambda shock, and this lambda shock keeps on moving downstream. So, for a given situation now just by changing the angle theta we can get another flow features which we call as a Mach reflections, and this particular flow phenomenon in which a lambda shock is formed, and we call this particular flow phenomena as Mach reflections. So, the special case can arise when the oblique shock solution is not possible for reflected shock from the solid wall. So, and with respect to corresponding Mach number M2, because the compression kernel causes the maximum flow deflection angle. Since the regular reflection is not possible, instead a normal shock is formed at the upper wall that allows the streamline to continue become parallel, but the very basic condition is that streamline must be parallel to this wall. So, to maintain these conditions of the parallel conditions, a situation is formed that a normal shock close to normal or very strong shock is formed. So, away from the wall, normal shock transits to a curved shock and intersect with a incident shock. Then what happens after that? The curved reflected shock, which is commonly referred as a lambda shock, propagates downstream, and it is this particular phenomena is referred as Mach reflection. So, it is a regular reflection is not a possible. So, we call this as a Mach reflection. The Mach reflection is characterized by large region of subsonic flow. Since it is a normal shock, we can say here if you look at with respect to region 2 and 3, Mach number in the region 3 could be highly subsonic, whereas in the region 2 can be supersonic, because it is a attached shock situation. So, the Mach reflection is characterized by a large number of subsonic flow behind the normal shock, and its analysis is not simple, because it involves lot of complicated flow phenomena, flow behavior. So, it is analysis normally carried out and then some numerical techniques, and it is not the part of the syllabus, but there are some physical phenomena or existence of this Mach reflection in many natural occurring process. Now, another interesting flow behavior of oblique shock situation, we call this as a wave reflection from a free boundary. Now, till this point of time, whenever we are talking about reflection, refraction or intersection, whatever may be, the oblique shocks are formed when there is a existence of a compression corner or there is a physical existence of a wall. But what will happen if there is no existence of this kind of physical boundary? So, then we can say it is a free boundary. Free boundary is another kind of concept which is similar to slip lines, and this free boundary is not a what we in our gas dynamic terms we call as a constant pressure boundary. So, it is similar to a slip line across which the pressures must match. Now, what will happen if a oblique shock is formed and it interacts with a free boundary? That means, there is no existence of a physical solid surface. So, one particular situation is given here, that there is a free boundary which is given by the dotted line, and this oblique shock comes and interacts. So, if you look at this particular flow behavior, this incident oblique shock interacts with a free boundary. Now, it try to gets reflected. Now, when it gets reflected, it does not appear as a oblique shock, because it becomes a expansion fan. That means, when an incident shock refers or interacts with a free boundary or constant pressure boundary, it reflects as a wave, expansion wave. That means, shock gets reflected as an expansion wave. So, what is the concept behind it? So, let us analyze this particular situation, that we have a situation where we have a constant pressure boundary P infinity and something like, and we have region 1 for which the oblique shock is defined. That means, shock wave is incident by a certain angle, and it is there is a shock wave angle, and this region 1 is defined. So, ideally the free stream boundary and initial region, the 1 is same, but when the streamline when it crosses the oblique shocks, the static pressure rises, because it is an oblique shock. So, static pressure rises. Now, when the static pressure rises, now after this the pressure boundary, that means, when it the incident shock reflects, you can see this constant pressure boundary gets reflected upward. When it gets reflected upward, you can imagine that it for this oblique shock it acts as a expansion corner. That means, for the streamline it acts as a expansion corner, because expansion corner, or you can have a imaginary convex corner. So, when there is an imaginary convex corner, so it must come out as an expansion waves. That means, streamline is going to get deflected through this corner. Okay. So, these streamlines goes deflected, and accordingly we will have a situation where P3, and we will have a situation in the region 3, and means region 3 also must match this pressure condition, that is P infinity, and the flow deflection line should also follow these similar directions with that, and so P3 must be equal to P infinity. Now, and since it is an expansion fan, so P3 must be less than P2. So, because P3 is less than P2, so there will be an expansion fan that is going to be formed. So, this is the concept behind that when an incident shock impinges a free boundary, it reflects as an expansion wave. So, whatever things I have said is that we have a incident shock when it impinges on a constant pressure boundary, the pressure in the region 1 is same as that of free stream pressure, while static pressure in this region 2 is higher due to the oblique shock. So, when this oblique shock hits this free boundary, its shape and direction is likely to change by preserving the free stream pressure, because free stream pressure is not going to change. So, this constant pressure boundary remains as it is, but its shape is going to change. So, the reflected wave must follow a fashion so that the free stream pressure must match with pressure in the region 3, that is the conditions after the wave and in this case the reflected wave at this impinging point must be an expansion wave. So, in this way what happens, the flow gets deflected by both incident shock and reflected expansion, causing the free boundary to deflect upward. That means, free boundary, as you see here, the free boundary is deflected upward. So, this happens when there is an oblique shock interacts with the free boundary. Another situation can have when there is an incident expansion fan. When there is an expansion fan, it hits the free boundary. So, as a result, if you can see here, it goes and this flow the flow is likely to get a turn when it this. So, instead of the free boundary getting deflected upward, it will be deflected downward. So, when it gets deflected downward, again there will be reflected expansion fan that is going to form, and finally this expansion fan is going to merge at a particular point, and after this merging point it again comes as a reflected oblique shock wave. And if you look at streamline point of view, it goes from starts from the region 1 and encounters the expansion wave, for which pressure rises in the region 2, and after this oblique shock formation again pressure is becomes still higher than P2. So, pressure is higher than P2, but it must match with the free stream pressure. So, this to match this and finally it has to finally P3 must be equal to P infinity, but since this P2 is less than P1 and P3 must be greater than P2 here, so as to match these conditions in the region 3. That means, this merging of this expansion wave must be a shock wave or oblique shock. So, that means, when this expansion wave comes and it merges as a reflected oblique shock. So, in analogous manner, if the incident shock wave incident expansion wave interact with a free jet boundary, it is reflected as a compression wave, and these finite compression waves quickly coalesces into a shock wave. So, this is the summary what we can have, and a typical classical example for this wave reflection from a free boundary, we can see a situation for a over expanded nozzle flow. So, in the subsequent down the line we will discuss about nozzle flow, and in a situation there will be a situation called as over expanded nozzle flow, and over expanded nozzle flow means that we have a conditions Pe is less than P infinity. Pe means when if you look at this particular nozzle, we can say that up to this point there is a solid boundary, and we can say the flow expansion takes place in a converging diverging nozzle, and exit pressure at this end of the solid boundary we say Pe. But when it comes and exit pressure, finally when the flow comes out the streamline, it sees a constant pressure boundary which refers to P infinity. Now, in a situation when P is less than P infinity, what is going to happen? So, and it sees the continuous constant pressure boundary, as you can see here, dotted line. Okay. And this particular shape is always followed. Now, what happens from the edge point at the exit point, we will have two oblique shocks. These two oblique shocks again interact, then again they will reflect as a oblique shock, or we can say refracted as a oblique shock, and finally after this meeting point it is a shock wave and it meets a free boundary. So, we will have expansion waves, and here also the shock wave, it meets a free boundary, it also have expansion waves, and these expansion waves goes further and meets, and though when they meet again they form a covalence single oblique shock. I will have a series of oblique shock that is formed in this manner. So, entire flow picture if you look at it, it follows a very specific pattern, and we call this as a diamond wave pattern. So, this was a very classical example which was represented in 1960s, and this diamond wave pattern is a very characteristic feature for a exhaust jet coming out of a over expanded nozzle. And this is a very interesting flow phenomena that occurs when there is a supersonic nozzle flow at the exit. So, at this exit what happens? Interaction of oblique shocks, expansion wave and free pressure boundary gives a particular pattern. This pattern we call as a diamond wave pattern. And finally, in summary, what I can say with respect to wave reflection from a free boundary, the following two general inferences can be made. First, the wave incident on a solid boundary reflect in like manner, that is compression waves reflected as a compression, expansion waves reflected as expansion. Wave incident on a free boundary reflect in a opposite manner, that means if a compression waves reflect as a expansion, expansion waves reflect as a compression. Okay. With this I conclude this entire concept of this module, and finally if I give a concluding remarks of this module 5, and in fact it is a very exhaustive module with consisting of 6 lectures, but what the very basic philosophy or the understanding that we get out of the module is that we start with theory of Frankel-Mayer expansion waves and oblique shock waves, theta beta m curves, and based on the theory we have seen the practical applications for the supersonic flow over wedges, cones and blunt bodies. We also give some understanding on shock expansion theory, where there is a simultaneous presence of shocks and oblique shocks, and this gives the concept of lift and drag theory in the design of airfoil. And another way of graphical representation that we made is shock polar and pressure deflection diagrams. These two diagrams are very vital to study some flow physics in the supersonic environment. So, what are the flow physics? They are regular reflections of oblique shocks, intersections of oblique shocks, we can have a Mach reflections, and apart from this we gave the concept of what is the solid boundary, what is a free boundary, what is the concept of slip lines. So, these are the overall feature of this module. Now, where these features we are going to use? So, in down the line at higher level of these things, though with aerospace community, these particular flow features are very vital when we are looking at supersonic flows or hypersonic flows in a duct or internal flow in a duct. So, normally this is the intake systems, this they are nothing but the intake systems of high speed engines, what we call as ramjet and scramjet engines. When such an engines gets fired, as I mentioned in my beginning lectures, these engines are there is no physical existence of any mechanical devices, they are entirely governed by through shock compression, shock based compressions, and of course continuous just by designing the geometry in the either it is a compression corner or expansion corner, convex corner. So, the duct systems are designed in such a way that we get our desired requirement as far as the thrust generation. But to get this thrust generation, the flow field has many instances. So, such instances that it could be a reflection, it could be a intersection, it could be the shock wave can interact with a free boundary, pressure boundary, all these things is understanding for these things is very vital. So, with this viewpoint, this particular chapter is very vital. And apart from that, there are also external aerodynamics. So, whatever Dog system, they are internal aerodynamics. There are also external aerodynamics, which means that we say that supersonic flow over blunt bodies. That means, shape of the aerodynamics or high speed vehicles are typically made as blunt bodies. So, where we have we can have a bow shock, we can have a expansion, or there can be localized compressions, localized expansions, that possibilities could be possible. So, with this understanding, I think this particular chapter is very vital in this particular course to understand the fundamental concepts of high speed engines, and in particular the intake aerodynamics of scramjet and ramjet engines. So, with this I conclude this module, and thank you for your attention.